lesson video for section 16.1, and as always, if you want my videos all in one spot, then just subscribe to my channel. So this lesson video is going to be kind of long. This section does have a lot of math and I do a lot of examples, so just bear with me on the length of it, not all of them are this long. So we're going to dive into energy, and mainly we're going to talk about heat energy, because chapter 15 will kind of introduce energy. So, thermal energy and matter. In the 1700s, most scientists thought that heat was a fluid called caloric that flowed between objects. So they thought it was an actual matter. Rumford studied the process of drilling holes in the barrels of cannons. So if they had like a big cannon, they would have to drill the hole for the cannonball to roll down. The process occurred in water so that the metal would not melt due to the heat produced. Because as you can imagine, when you have metal trying to drill into another metal, then there's a lot of friction, a lot of heat that's produced, and so that could cause one of the metals to melt. Rumford discovered that the heat was a result of the motion of the drill, not a form of matter. So he's the one who first figured out that heat was not an actual fluid, it's a form of energy. Some of the work done by the drill does useful work, because it actually does drill the hole that's supposed to. But some energy is lost due to friction, and that's what we talked about when we talked about simple machines, is you never get the same amount of work out as you put in. So heat is the transfer of thermal energy from one object to another because of a temperature difference. And heat flows spontaneously from hot objects to cool objects. So a lot of times if I ask you what direction heat flows, y'all want to say it flows up because you think hot air rises. But the actual terms that we use is it flows from hot to cold. Okay, it always flows from hot to cold. Temperature is a measure of how hot or cold an object is compared to a reference point. The actual definition for temperature is it's the average kinetic energy of the particles, but our physical science book kind of goes into a super basic definition, what I like to call an elementary definition. So temperature is related to the average kinetic energy of the particles in an object due to their random motions through space. So remember, we talked about the faster the particles move, the higher the temperature. The slower the particles move, the lower the temperature. As an object heats up, its particles move faster on average. So thermal energy is the total potential and kinetic energy of the particles in an object. Thermal energy depends on the mass, the temperature, and the phase. So is it a solid, liquid, or gas of an object? Okay, so mass, temperature, and the phase, or state of matter. Thermal energy, unlike temperature, depends on mass. Okay, because the more mass an object has, if I have a small object at 100 degrees Celsius and I have a large object at 100 degrees Celsius, because it's the combination of all the particles' energy, the large object will have more thermal energy even though they have the same temperature. So slower particles collide less often and exert less force, so pressure decreases and the object contracts. As you slow the particles down, they get a little closer together, and so objects will contract as they get cooler. This is called thermal contraction. And of course, as things get hotter, they expand, okay, because the particles move faster, and so it spreads out. So thermal expansion is an increase in the volume of a material due to temperature increase. Thermal expansion occurs when particles of matter move farther apart as temperature increases. Gases expand more than liquids and solids. Solids expanding the least. So all of the states of matter will expand and go through thermal expansion and contraction, but gases are the most visible to see the difference. However, you can see it in a solid. If we look back at my previous slide, this right here, you see how wavy these train tracks are? What that means is they put them too close together. They should have left a little gap in between them, because as it gets really, really hot in the summer, those rails expand and they don't have anywhere to go. So that's why they became all wobbly in this example, was they didn't leave the correct spacing. So thermal expansion is used in glass thermometers. As temperature increases, the alcohol or mercury, depending on which kind you're using, in the tube expands and its height increases. Okay, so if you see a thermometer and it has like a red or a blue liquid in it, that's an alcohol thermometer. If you see the ones that have the silver, that's mercury thermometer, and mercury is poisonous. So most of the time at school you'll use an alcohol one. So as you heat the liquid, it will expand, and so it rises and shows the correct temperature. As we cool the liquid, it will contract and go back down the thermometer. So specific heat is the amount of heat needed to rise the temperature of 1 gram of a material by 1 degree Celsius. The lower the material's specific heat, the more its temperature rises when a given amount of energy is absorbed by a given mass. Specific heat sometimes is a little tricky for students to understand, so I always say think about a swimming pool. It's a hot day outside. the same sun is shining on the swimming pool as on the concrete around the swimming pool. But when you run outside to go jump in the pool, that concrete is hot. But when you jump in that pool, the pool is not. But the same sun, the same amount of energy is entering both substances, so why aren't they the same temperature? Well, they have different specific heats. The concrete specific heat is lower, which means it takes less heat to make it increase in temperature. Water's specific heat is higher, which means it takes more energy to increase the temperature the same amount as the concrete. So it's a difference in specific heat. That's why also when you're like cooking something in the oven, like think about, or like the microwave, like a Hot Pocket, you'll feel the outside and you'll think, oh, okay, this isn't that hot, and then you bite into it and the inside's like on fire. It's because of the different specific heats of the substances. So our formula for calculating heat is Q equals MC delta T. Now I know this is weird, but heat is represented by Q. So heat is Q because it's a form of energy, it's going to be in joules. M is mass, it's going to be in grams. Now I know when we focused on other forms of energy, mass was in kilograms, but for heat, mass is going to be in grams. C is the specific heat or specific heat capacity, that's where the C comes from, and it has 3 units. It's joules per grams degrees Celsius. And then delta T, delta always means change in, final minus initial. It's the change in temperature, and it's always the final minus the initial temperature, and it'll be in degrees Celsius. So don't do initial minus final. It's always final temperature minus initial. So let's look at how to use this formula. Whoop, oh gosh, well my answer already came up. Okay, well I'll just verbally explain this one then. All right, so an iron skillet has a mass, let me grab a marker, has a mass of 500 grams. The specific heat of the iron is 0.449 joules per grams degrees Celsius. So specific heat is my C. So you have to be careful. My students usually get C and Q mixed up. C is specific heat, Q is heat. And specific heat has the weird units, Q is just joules. How much heat, so I'm looking for Q, must be absorbed to raise the skillet's temperature by 95 degrees Celsius. So they didn't give me a final and initial temperature, they just gave me the temperature change right there. Okay, so Q equals M times C times delta T. And so here's my MC delta T, so I just plug in. So it's my M times my C times my delta T. And so if you look, this grams and joules, this grams and degrees Celsius is on bottom. So grams cancel, degrees Celsius cancel. So the unit I'm left with is joules, and once I multiply across, I get 21,327.5 joules. Alright, so hopefully that one's not too bad. Like I said, the main thing that my students do is they mix up Q and C. So Q is heat in joules, specific heat is C, and it's joules per grams degrees Celsius. Alright, so let's move on and look at some more. Hopefully my answers don't just come up immediately. Don't know what happened there. Oh well. Ah, there we go, that's better. Alright, so it says how much heat, so I'm looking for Q, is needed to raise the temperature of 100 grams of water, so there's my mass, by 85 degrees Celsius. So there's my change in temperature. Specific heat is 4.18 joules per grams degrees Celsius. So there's my C. So again, I'm solving for Q. I don't even have to rearrange. So Q equals MC delta T, so my mass is 100 grams. My specific heat is 4.18 joules per grams degrees Celsius. And my change in temperature is 85 degrees Celsius. So Celsius cancel, grams cancel, and once I multiplied, I got 35,530. And the unit I'm left with is joules. Alright, so hopefully that one was a little better since I actually got to show it to you. Alright, so maybe pause and try the second one. There is a little trick on the second one with the kilojoules, but maybe at least try to get joules on your own and then watch it and we'll solve it together. So it says how much heat in kilojoules. So I'm still looking for Q, but I'm going to circle that I need to have kilojoules because my answer is going to naturally be joules. Is absorbed by a 750 gram iron skillet, so there's my mass, when its temperature rises from 25 to 125. Okay, so my delta T is my final temperature minus my initial temperature. So it goes from 25 to 125. So it's going to be 125 minus 25, so of course my temperature change this time will be 100 degrees Celsius. So if they give you the two temperatures, you have to remember to subtract. Alright, so there's my temperature change, but you'll notice C is missing. Well, I gave you C in one of the previous questions for iron. It was 0.449 joules per grams degrees Celsius. Okay, I just pulled that from the previous question. You'll always be provided C. Don't think you have to memorize those. Alright, so I'm going to solve. Sorry, Q equals MC delta T. So my M, of course, is, look, where is it? There it is, 750 grams. My specific heat is 0.449 joules per grams degrees Celsius. And my change in temperature we decided was 100 degrees Celsius. So Celsius and grams cancel. I'm left with joules. And so once I multiplied, I got 33,675 joules. So my answer is in joules, but the problem is it wants kilojoules. So we all know, or you should know, kilo equals 1,000. So 1 kilojoule equals 1,000 joules. So if I know that, I can just convert it. So we can do 33,675 joules, and then I can say, well, 1,000 joules equals 1 kilojoule. So joules cancel, and so then I end up getting about 33.675 kilojoules. Or you could round that if you want to like 33.7 kilojoules. The other way you can do it is if you know how to move the decimal. If you know 1,000 joules in a kilojoule, you move the decimal 3 places. So you can just go 1, 2, 3 like that, and see then you still get 33.675 joules. So make sure you know how to convert kilojoules to joules, because that's sometimes a question I'll ask. Alright, so hopefully you got that one right. At least the joules part, the kilojoules part might have kind of messed you up a little bit. Gosh, my marker didn't want to erase well. Oh well, we don't have time to waste in the video to watch me erase. Alright, so let's look at a couple more, because sometimes you're going to have to solve for other things besides Q, and that's where we have to rearrange the formula, which some of y'all aren't quite that good at. Alright, so let's look at some of those. So in setting up an aquarium, the heater transfers 1,200 kilojoules of heat. So there's my Q, but my issue is going to be it's in kilojoules, I need it to be in joules, to 750,000 grams of water. So there's my mass. What is the increase in the water's temperature? So I'm looking for delta T. So you may be thinking to yourself, well, where's C? Well, remember, we just did water in one of the previous examples. So C for water is 4.18 joules per grams degrees Celsius. So that was just from one of the previous questions. All right, so the problem is when I plug in for Q, I have to have joules. I can't have kilojoules. So again, I'm going to need to change this. So 1,200 kilojoules, well, we know 1,000 joules is in 1 kilojoule. Or if you know how to move your decimal, you know you can move your decimal 3 places. And so it should give you this right here. Okay, so you should get 1,200,000 joules. So let's look at how to rearrange this formula. So we have Q equals MC delta T. We need to solve for delta T. So I need to move M and C to the other side. So I do the opposite mathematically. So right now everything's multiplied. So what's the opposite of multiplying? Dividing. So I divide both sides by M and C. And so then I get delta T equals Q divided by M and C. And so then I just plug in. Oh, marker's dying. So my Q, remember we changed it to joules. So it's the 1,200,000. Make sure I have the right amount of zeros. Divided by my mass, which is 75,000 grams, times my specific heat, which was from one of the previous questions. And you may want to put those bottom numbers in parentheses, depending on what calculator you're using. So if you look, joules cancels, grams cancel, and I'm left with degrees Celsius, which makes sense because I want change in temperature. And when I multiplied and divided and everything, I got 3.8 degrees Celsius. So the main thing that people have trouble with in this chapter is this formula right here. Alright, so maybe pause it, try this one on your own. Remember, you have the specific heat of water right there. Alright, and then we'll do it together. So it says, what mass of water? So this time I'm looking for M. We'll change its temperature by 3 degrees Celsius, so there's my delta T. when 525 joules, so there's my heat, is added to it. So remember, we can use the same C that we have for water up here. So it's 4.18 joules per grams degrees Celsius. So I need to rearrange my formula and solve for M. So Q equals MC delta T. If I want to solve for N, I need to get C and delta T to the other side, so I do the opposite. Right now, we're multiplying by them, so the opposite of multiplying is dividing. So I divide both sides by C and delta T. So mass equals heat over C times delta T, and then I just plug in. So my heat is 525 joules. My specific heat is 4.18 joules per grams degrees Celsius, and my change in temperature is 3 degrees Celsius. So if you look, our joules and our Celsius cancel, and so we're left with grams, which makes sense, we're solving for mass. And so when I solved, I got 41.9 grams. Just like that. Alright, so hopefully you got that one right on your own. This one didn't have any tricky stuff about the kilojoules. Alright, so let's erase and move on, as we should be getting close to the end of the section. Hopefully I can do better at erasing. I don't have very strong arms, obviously. Oh my gosh. Yeah, the erasing is not going well today. Clearly I need to use a different marker. Oh well, we'll just bear with it. Maybe y'all can't see it as much as I can. Alright, so calorimeter, like I said, anything green, other teachers have told me is not on the EOC, so I've skipped over it. So let's knock out this section assessment. So in what direction does heat flow on its own spontaneously? From hot to cold. From hot to cold. How is the temperature of an object related to the average kinetic energy of its particles? The higher the kinetic energy, the higher the temperature. So you could say they're directly proportional. If one goes up, the other goes up. If one goes down, the other goes down. So you can say they're directly proportional. Name 2 variables that affect the thermal energy of an object. Well, we listed 3 in the PowerPoint, but you could say mass, you could say temperature, or you could say state of matter. Any of those 3. Well, I mean, pick 2 of those 3. All right, so mass, temperature, and state of matter, or phase. Next one, what causes thermal expansion of an object when it's heated? Well, when it's heated, the particles move faster and they spread out. Okay, so it's that spreading out that causes an object to expand when heated. And of course, when you cool it, they slow down, get closer, and then it'll contract. All right, so it's the particles spreading out. So how do the temperature increases of different materials depend on their specific heats? Well, remember, the higher the specific heat, the more energy it takes to increase the temperature. All right, the higher the specific heat, the more energy it takes to increase the temperature. So what that means is 2 objects can absorb the same amount of energy, but their temperatures won't necessarily change by the same amounts. All right, we can skip this one because it's based on the calorimeter, which we don't cover. So why is it necessary to have regularly spaced gaps between sections of concrete sidewalk? Well, remember, that sidewalk is going to get really hot in the summer, and what's it going to want to do? It's going to want to expand. So if you leave the gaps, you have less cracking. Okay, so you can say that it's necessary to reduce the cracking due to the thermal expansion. Okay, it's necessary to reduce the cracking due to the thermal expansion. All right, and then 2 more problems. My gosh, I was just full of sample exercises on this one, wasn't I? All right, so it says the specific heat of copper is 0.39 joules per grams degrees Celsius. So there's our C. How much heat, so we're looking for Q, is needed to raise the temperature of 1,000 grams, so there's my mass, of copper from 25 to 45 degrees Celsius. So remember, change in temperature is our final minus our initial. So my final temperature is 45 degrees. My initial temperature is 25 degrees. So that's going to give me a delta T of 20 degrees Celsius. All right, because I'm solving for heat, I don't have to rearrange my formula. So Q equals MC delta T. So then I just plug in. So my mass is 1,000 grams. My specific heat is 0.39 joules per grams degrees Celsius. And my change in temperature is 20 degrees Celsius. So my degrees Celsius and grams cancel. I'm left with joules. And so when I solved, I got 7,800 joules. 7,800 joules. Okay? So again, maybe pause it, try this one on your own, and then we'll look at it together. Don't forget, specific heat of water was on the previous slide. It's 4.18 joules per grams degrees Celsius. So try it, we'll look at it together. It says a peanut burned in a calorimeter and it transfers 18,200 joules, so there's my Q, to 100 grams of water, so there's my mass. What is the rise in water's temperature? So I'm looking for delta T, and so I told you from our previous slide, C for water is 4.18 joules per grams degrees Celsius. So this one we are going to have to rearrange our formula, but hopefully you're getting used to that. So Q equals MC delta T. So if I solve for delta T, I need to get rid of M and C, put them on the other side. So how do I do that? I divide, because right now we're multiplying by them. So delta T equals Q over M times C. So then I'll just plug in. So my Q is 18,200 joules. My mass is 100 grams. And my specific heat is 4.18 joules per grams degrees Celsius. So our joules cancel, our grams cancel, we're left with degrees Celsius. And so once I solved, I got 43, whoops, this should be an equal sign, 43.5 degrees Celsius. Alright, so I apologize about the length of this video, but there was a lot of examples of Q equals MC delta T, because that's a formula that my students just normally struggle with. Alright, so hopefully you understand a little bit more about heat, how it flows, its units, and how to use Q equals MC delta T.